So all of this brings us to the notion of metrology and why it's important in managing quality. Metrology is the science of measurement, and it refers to the collection of people, equipment, facilities, methods, processes, everything that we use to make sure that measurements are correct and that we collect enough information or enough measurements. Um, a lot of the companies to be able to trade nationally and internationally, they must satisfy requirements that are set by um, standards, laboratories, organizations, accredited calibration laboratories, and establishments similar to those. Unless they have those um, verifications from these types of institutions, they're not able to trade and they will not be able to conduct business. So, two dimensions of measurement that are very important and that must be studied is accuracy and precision. Accuracy of measurement is how far off is the true value for that quality characteristic that we want. How far off is the true value of it from the average of measurements that we take. So if I take several measurements and I average those measurements, the difference between that and what the true value is the accuracy of my, or lack of accuracy of my measurements. And accuracy is generally reported as the amount of error in measurement relative to the total measurement, to the total size of the measurement. Precision, on the other hand, is how close are repeated measurements to each other. So how consistent am I as I'm doing my measurements over and over again. Here is a graphical representation of accuracy and precision. If the target value is right here, then we can see that for these measurements, for one thing, it's not very accurate because we're missing this target. And then you can see that the distribution of the measurements is pretty wide. It ranges from here to here. So this one is not accurate and it's not precise. View graph B, you can see that it is not accurate at all. Here is the marker for true value and we've completely missed it. But you can see that the distribution of the measurements is not so wide, at least not as wide as part A. So this one is better in terms of precision, but not accurate at all. For C, we can see that it's better in accuracy because all the measurements fall around the true value, but you can see that the distribution of the measurements is very wide. So this one is not as precise, but it is more accurate than the other two. And then this one, it's pretty much very good in terms of its accuracy because the measurements fall all right around it, and the distribution is not very wide in terms of the measurement. So this one is more accurate and more precise than any of the other ones. What's important to note is this, that if measurement is precise, we can't assume that it is accurate or vice versa. So all of this relates to repeatability and reproducibility analysis, which a lot of the times we call it R&R studies. So repeatability, as the name implies, relates to or refers to equipment variation. So if the same person uses the same instrument to take multiple measurements. So it's the same individual, so his or her knowledge or expertise or training is consistent, and it's the same instrument, so we're not changing the instrument on the individual, and that individual uses the same instrument to take multiple measurements. So if there is variation, then it would have to be due to the equipment, or at least we would make that assumption. Reproducibility, on the other hand, refers to the appraiser or the operator, to the variation that we might have due to the operator or to the appraiser. So the reproducibility is measured when different people use the same instrument to take the measurement. So it's the same device, same instrument, and different people use it. So in this case, because the device is constant and we're using different people, any variation that in our measurements would have to be attributed to the operator or to the individual. So in an R&R study, we use statistical analysis to understand variation in measurement systems and also the sources of variation in measurement. Basic steps in R&R studies is we select so many operators, we select so many parts, we calibrate the measurement device or the instrument, we randomly measure each part that we have selected by each operator, and we repeat that for so many trials. And then we compute key statistics to quantify the repeatability and the reproducibility of the system. So R&R statistics usually are given by these. These are equations 817 to 820 in your book. And your author says that this is a pretty good rule of thumb for interpretation of those. The thing is that, as you recall, we said R&R equals the equipment variation and the individual or the appraiser or the operator variation. So these two combined, this one and this one, will result in this one. But because in this case we're not squaring all these differences, then the R&R, percent of R&R and percent of the part variation do not add up to 100%. So we do want these two to add up to 100%, because then interpretation of that, it would be so much easier for the operators and for the managers. And so one method that we can use to accomplish that is by computing a ratio of variances by using these equations that are in your book. So when we compute these as ratio of variances, so the same information that we had used before but expressed somewhat differently just by squaring things, and now you can see that again these two will add up to this, but then the summation of this item and this item, the R&R percent of total variance and the part variance as a percentage of total variance, now these two add up to 100%. And so it'll become a lot easier to distinguish and say, is most of my variation due to the product itself or to the part, or is it because of R&R and my people who are doing the measurement, or because of the actual equipment that I'm using for my measurements. So here is an example that your book has. I'm not going to go over it. The thing is with R&R is that it's a lot of tedious calculations, And so the author for this book has created these Excel templates. And so you can, I'll take you quickly through this Excel template for reserve problem 8.3. Data is collected, and we know that this is our target, and we know that from a specification perspective, the upper and lower spec limits are 1.15 to 1.45 given this information. So with that, then all that we must do is populate. Well, let me show you this is the actual data itself. You can see that we have 3 operators. You can see that we have 3 operators. Each operator does 3 trials, and there are 10 parts that we have the operators measure. And so we have this data. Manual calculations would amount to all this that you see here, and it's just too tedious. It's not very difficult to do, but it's very tedious, and you would be prone to making errors. And so the authors have developed this this template where you can insert the number of operators, the number of trials, the number of parts, and then the upper and lower spec limits, and then of course the data itself. So all of these yellow cells must be computed. And so what you can see is the outcomes will pop up. And this is what I was talking about earlier, that these percentages, these right here, and then these percentages do not add up to 100%. Okay, like this one and this one. And so that's very difficult to understand for a lot of people. And so when we express the variations as variance of ratios, then we can, or variance ratios, then we can see that the R&R and I should probably increase that. You can see that the R&R and parts variation adds up to 100%. And so just looking at this, we'll see that the equipment is a source of a problem here. Operator, perhaps not so much relative to everything else. And so the summation of those two gives us the R&R, and then the balance of it to 100% is the parse variation. So in this case, from an R&R perspective, we should investigate and see whether the devices need calibration, or whether we're using the right devices for our measurements, or a whole host of issues could be explored. And it seems like in this case that the product or the part also needs to be looked at in terms of the variability that it has inside of it. Another way that we can look at this is using this upper control limit for individual ranges that can be computed. And as you can see, this is the upper limit for all the individual ranges, and as long as all of our ranges for each operator and for each for each operator are within that that control limit. So all of those ranges were less than this control limit. So from this perspective, we can see that perhaps we don't have too much of an issue with R&R, but since our variance ratios indicated that R&R is at 51, 52%, perhaps we should take a look and see if there are sources of variation that can be minimized.